I am going to introduce you to what is buckling analysis. So what is buckling? So what happens if we have a long slender structure like this and I apply some compressive force over it? What happens? Even the stresses that are present inside this particular body doesn't cross the yield limit of the material, this body is going to be failing. So why it is failing? It is failing due to the formation of excessive deformations. So this particular phenomena is known as buckling. So you can see many structures require an evaluation of their structural stability, especially thin columns, compression members, vacuum tanks are different examples of the structure where stability considerations are very important in designing those structures. Then on the onset of the instability, say the buckling of a structure, what happens? A large change in the deformation occurs, but the load that is applied on that particular structure is not going to change. So this particular failure or this particular characteristic may be called as the stability or structural stability of the product, and we need to study this before finalizing the design. So why buckling analysis is performed? Buckling analysis is performed to predict the failure of objects under excessive deformation. This mainly occurs due to the structure losing its stiffness in a certain direction, even though the stresses doesn't come even close to the failure stresses. As I've told you, if we take a long slender structure and we apply the compressive force on it, what happens? In this vertical direction it is going to lose its stiffness and it is going to have a very high deformation, which is leading to failure, and this particular phenomena is known as buckling. And this particular analysis is majorly applied for long structural members and thin walled structures with very thin walls. So for example, let us say a pressure vessel, then columns, building columns, etc. So coming to eigenvalue or linear buckling analysis, it is used to predict the theoretical buckling strength of an ideal linear elastic structure. So what happens? The eigenvalue buckling solution of an Euler column will be exactly matching with the classical Euler solution. But what happens? Imperfections and nonlinear behaviors prevent most real world structures from achieving their theoretical elastic buckling strength. So linear buckling generally yields unconservative results by not accounting for these effects. Although unconservative, linear buckling has an advantage of being computationally cheap compared to the nonlinear buckling solutions. Different assumptions taken for linear buckling analysis. The first and foremost assumption is the stiffness and the stress are constant and linear elastic material behavior is assumed and small deflection theory is used and no nonlinearities are included. So if you are going to select the large deflection theory to solve this particular problem, you are going into a nonlinear zone. And for a linear buckling analysis, the eigenvalue problem is solved by using the equation of k plus lambda I into s psi I equal to 0. And it is important for you to remember all of these assumptions while performing a linear buckling analysis. Then applications of linear buckling analysis. As we have seen earlier, it is going to be applied in a lot of areas like aerospace, automobile, marine, sports, construction, offshore structures, etc. All the fields where FEI is applied for studying long, slender structural members and thin walled structures that are subjected to compressive loads, then we are going to compulsory perform linear buckling analysis, because we first perform the linear buckling analysis to understand the behavior and then change the design, and once we are satisfied with the design, then we are going to go for the non-linear buckling analysis if required. In the next lecture, I am going to introduce you to buckling analysis inside ANSYS workbench. ANSYS workbench. So how to access eigenvalue buckling analysis? So for this you need to perform static structural analysis first, and then you need to take these particular loads and transfer these loads into eigenvalue buckling analysis system, so that you are going to perform a structural buckling analysis. Then coming to thermal buckling analysis, you can take a thermal system and place it over here, and then you can transfer these loads to static structural system. Then from there you are going to transfer these loads into eigenvalue buckling, so that you will be able to perform what is known as a thermal buckling analysis. So what are the different types of geometries that can be used to perform buckling analysis? We can use solid bodies, we can use surface bodies. As I've told you previously that for the surface bodies we have to define the appropriate thickness, and we can also use the line bodies for which we need to apply the appropriate cross sections. See, only buckling modes and displacement results are available for line bodies. Then for material properties, you need to define Young's modulus and Poisson's ratio in order to perform a linear structural buckling analysis. And if you are going with linear thermal buckling analysis, in addition to Young's modulus and Poisson's ratio, you need to define the thermal conductivity and coefficient of thermal expansion alpha. Then coming to the loads and supports, all type of structural loads can be applied on this particular bodies in order to perform a buckling analysis. Compression only supports are not recommended in this particular type of analysis. The structure should be fully constrained to prevent rigid body motion and in order to get good results. So what happens in buckling analysis, all the applied loads F are scaled by a multiplication factor which is lambda until the critical buckling load is reached. So coming to the buckling analysis procedure, we are going to take the static structural and we are going to perform this static structural analysis, and from that we are going to transfer the loads to the eigenvalue buckling analysis, where we are going to find out the critical buckling load as well as this multiplication factor and the shape in which this particular object or the product is going to buckle. So coming to the results, if we are going to perform a linear buckling analysis, it is going to take more time and more computation resources when compared to the static analysis for the same model. Once you go to the solution information branch, you are going to have all the details of this particular solution. Then once the solution is completed, we can view the buckling modes. So what happens, we are going to get a load multiplier for each buckling mode, and if you take this particular buckling factor which is denoted by the lambda here, so in order to find out the buckling load or buckling force, we need to multiply this lambda into the force that is applied onto this particular body. So how we can interpret this load multiplier? So one thing is, we can solve every model for two times. First case is we are going to apply a unit load, and in the second case we are going to apply the expected load. So what happens, first we are going to apply a unit load, we are going to get a what is known as a multiplication factor, and we are going to note it down, and then we are going to apply whatever the real force that we are assuming that will act on this particular body, and then we are going to solve it once again. Then what happens, you are going to get a multiplication factor. This can be done in order to compare both of the results and say whether your analysis is right or wrong. If you want to find out the buckling load, what is happening, you need to multiply this lambda into unit load if you have applied the unit load, or otherwise what happens, if you have applied whatever the load that is being put on that particular body, you need to multiply that particular value into lambda in order to get a buckling load. Then buckling load divided by the actual load is equal to lambda, and this lambda is nothing but the safety factor. We are going to observe all of these things while we are solving buckling problems using ANSYS workbench. In the next lecture, I am going to take up a pipe model and demonstrate how we can perform buckling analysis inside ANSYS workbench.